All right, welcome to 168. To this course is a finite element course, and I hope that you do enjoy this class this coming quarter. My name is Vinay Goyal, and I've been lecturing here since 2009 for Professor Klug and other professors as well. And so one of the things I wanted to tell you about is that I really demand a lot from my students, as some of you know, but I think you'll learn a lot. And I think if you put the effort required, that you'll succeed and you'll learn a lot. That's my goal. I want to introduce you also to Leonardo. Leonardo will be your TA, and also you'll have a grader as well, which I don't know who that is yet. Leonardo's responsibility will be to help me make sure this class runs smoothly. It's not an easy class to teach, and so hopefully we can both succeed in here. Also, I do value a lot, people working together. I really think there's value in that, and if you have the opportunity to do, I really recommend it. It's a great way of learning. You can learn from others, and others can learn from you. Anyway, I do have a quote that I always call out: is high achievement always takes place in the framework of high expectations. So my expectations are high for each of you because you are at a top-notch university. And so, I'm going to expect the most from you, and I hope you can reach to that level, okay? I do want to dedicate this course to my mentor, my friend, Professor Klug. He's the one that gave me the opportunity to teach here. I tremendously miss him every day. It's hard, okay? So please work hard in honor of him, all right? That's the least you can do. Work hard because he's somebody that wanted the best from his students, okay? Well, I'm the instructor here. That's my email. You can email me anytime. I will respond immediately. Within 24 hours, maybe not immediately, but I'll try my best to respond to you in a timely fashion. My background, I worked for NASA initially. I worked for Aerospace Corporation, and I have over 20 years of experience working with finite elements. So I'll try to make some connections to real-life experiences so you understand how things connect. And hopefully when Leonardo also goes through his lab session, he's able to draw some connections. We'll try to create some problems that are of interest in the industry here. My expertise is failure analysis of aerospace vehicle, airplanes, aircraft, launch vehicles. My expertise is failure of composite materials. That's where I did my work, my research. And I also enjoy a lot developing new techniques for finite elements. And so if your area of research was that, I can also help you out in whatever I can. Office hours, my approach with office hours is simple. Right after class, if you have questions, I'll be here as much as you want, and we'll just have a good time here. I also sometimes reach a little bit earlier in class. You can reach me there. I also am very responsive to email, and I also use the class forum quite a bit, so that's an area that you can also help each other out. For example, say one of you having a question, the other person can respond immediately also. We also have Leonardo. I'm not sure what the office hours for you are yet, but hopefully you can post that for them to know.
Yeah, they are going to be posted.
Great. And so we both can be of help and help you succeed. That's my goal for you. Actually, my goal for every one of you is to get an A in this class. If you have less than an A, it's a failure for me, because to me an A means that you learned, right? So that's really the goal for me, for each of you, okay? The objectives of this course. I want you to develop a sound understanding of the fundamental theory and the mathematics behind finite elements. And the second part of this is not just a theory, because theory is one thing, but how you apply it in real life is another thing. So the second aspect of this course is to gain experience using, in this case, we're going to use a software called Abacus, CAE. And in this software, you can probably solve, very complex problems. I mean, I use this at work almost daily. But you can also use other software like Nastran, ANSYS. There's a large number of software out there that can help you also succeed. But for this course, we'll be using Abacus to try to learn how to use it the best way possible. Okay, so moving on, the format of this course is the focus on the lectures here are the theory and the mathematics. I'll try to give examples how this could be used in practice also sometimes. But the real practical experience comes from using Abacus, and that's where you'll be participating in the lab sessions. I'll provide assigned reading assignments to each of you through class forum or announcements. There's 2 textbooks for this book. They're both free. Both PDF files that I have uploaded already for your experience. One of them I co-wrote with my brother. Is pretty extensive, really deep into finite elements. I go into a lot of different things, axisymmetric modeling, things that I may not be able to cover here. But to me, if you get a fundamental understanding, then you can follow the book on your own even. We also have the textbook for this course, which was written by Professor Klug, and we'll use that as well. So both of these books are basically provided to you. I also recommend buying a book from Amazon.com so you can get a third experience. And so for that, we can, if you have questions about which book to get, we can talk about it at the end of the class. There's many different books. One approach is buy the cheapest and see how it goes, right? Website, I will be providing these handouts for your experience so you can read them, go through them. I'll post the homework. We're already devising a homework for you for next week, but maybe I'll wait till Thursday. I'll put announcements there, and any other information will be communicated there. Excuse me. The usage of software, my goal here is not to teach you how to program. I will expect that everybody here can at least learn how to do it. And if you haven't done it, maybe work with somebody that's done it and try to learn from them. And maybe Leonardo can also help a little bit. But I want Leonardo's time to be focused on the theory and application, not helping you code stuff up. You can also download Abacus for free. There's a student edition online that you can download. I give you the website here. If you submit a request, they'll give you access. Within a couple of days, you can put it in your own laptop. Okay. Continuing here, the homework is a significant portion of this class, 34%. Weekly homeworks will be provided. I do encourage working together. If you have partners that you want to work with them. But at the end of the day, you submit your own work. So you're not copying each other's work. You're working, on the concepts of the class and trying to succeed together. I do recommend writing on one side of the paper and very clear so my graders and TAs can grade you appropriately. Otherwise, it's difficult for us to grade you. Okay? Not late homeworks will be accepted. I don't accept homeworks that are late. If you have a commitment, start early. Don't wait to the very last minute. In fact, some of my best students, which are actually sitting here, some of you are here, that took my other classes, they will start the homework, I think, the same day. And then the next day they encounter me, they could ask me all kinds of questions, right, in person, and we could even, sometimes I can even give them very good clues on how to go about it. Okay, so two exams, one midterm, one final. The midterm typically midway, of course, week number 5 or 6. I haven't decided whether it will be a take-home or in-class, depends upon the complexity of the homework. If it's in-class, it will be simpler, but then close notes. If it's take-home, a little more complex, but still doable. Final exam as well. Attendance is mandatory for this class. I do provide all these lectures, and there's video lectures as well that will be available to you to review on your own time. Part of me is my first time doing a video lecture, so if I'm not clear through video, we'll improve it as we move forward. I do think honesty develops early from childhood and continues as you move forward in life. And I do think it's very important for you to demonstrate these characteristics because that's a major characteristic for engineer. You know, good ethical behavior and also ensuring that you have good professional integrity. As you move forward in your profession and industry, these things will become important, very important. Okay, so I'll enforce this to the strictest extent possible. Finally, I will continue here. The contents of this course will have in general the basics of approximation theory. I'll start with 1D, 2D, and then I'll move to 3D. Once I cover 1D and 2D, 3D is easy. We'll discuss discretization and interpolation. Right now, you probably don't know what I'm talking about, but I'll show you what I'm talking about later. We'll cover 1D, 2D, and 3D elements. And then we'll go to isoparametric formulation. And then we'll talk about practical modeling considerations. And finally, I'll show you how to interpret the results you're getting from the code in a way that makes sense. Okay? The outline of this course will start today. I will start with that today, with the history, the motivation and overview of finite elements. And I'll start with Springs today. And I'm hoping to actually cover significant amount of the lecture on Springs. And I'll move very quickly to approximation theory. I'll cover strong form Galerkin, weak form Galerkin, and if I have time, I'll move to Riley-Ritz. Then I'll go to 1D isoparametric formulation for bars, trusses, 1D interpolation, Jacobians. We'll cover some heat transfer problems, some elasticity problems, and then we'll cover how to assemble these elements together. And then I'll cover 2D and 3D isoparametric formulations, quadrilaterals, triangles, and so forth. Then we'll talk about errors, sources of errors, errors estimation, mesh refinement, and convergence. And what I'm hoping to cover towards the end is dynamics, buckling, and axisymmetric elements. And so some of you who took 261A with me, you pretty much know most of this stuff, but you will see a different perspective when you take this course and learn other things that I did not have time to teach there. Great. That was it. That's the outline, and that's the syllabus. That actually is the syllabus of the course. I think some of you were asking for it, but now you have it, and I'll post it today. Here is the two books. There's, can you see the here? So this is one of the books, and if you are going to start reading, sorry. If you're going to start reading, which I really recommend doing, you want to start with chapter 1 and work your way down. So do chapter 1 right here. Skip overview of continuum mechanics. So skip that. But look at finite elements and then go to approximation to differential equations. So go there directly. Read strong form Galerkin. That's where you want to focus your time. Okay. Starting today. I mean, I expect everybody to start studying today. That's the goal. Okay, and then we have another book. These are free books. I'm not asking you for a lot of money here. It's free books. So let's take advantage of this opportunity here. And this is the other book that you shall start studying. And so hopefully with these two books we will be in good shape. Plus the lecture notes. All these three things will help you, I believe. Let me go right through the next lecture here, the history and motivation. Okay? And so what is finite elements? Finite elements is an approximation technique, and it provides you a systematic approach to solving partial differential equations for a wide variety of problems. And it's extremely amazing because you can solve virtually any PDE, any partial differential equation you want for heat transfer, solid mechanics, fluid mechanics, electromagnetics. You can do coupled. You can couple all these things together and any other PDE, partial differential equation you want to dream about, you can use finite elements. And with finite elements, what finite elements has allowed us to do is to discretize the solution to a partial differential equation in a way that allows us to solve it in a simple way. And I'll give you an example of that coming up. Okay? Here, what we need to be very cognizant of is what are the variables of interest. So when I look at a heat transfer problem, what is the variable of interest?
Source.
Sorry? When I'm looking at a heat transfer problem, what is the variable of interest that I'm solving for? The temperature field, right? When I'm looking at a solid mechanics problem, the variables of interest I'm solving for are displacements. And from displacements, I can get strains, and from strains, I can get stresses. Okay? So these are the variables we're trying to solve for using finite elements. Okay? The motivation behind FEM is that, I'll just click all the way down, is to solve real problems, real complex problems. Complex geometry, complex material properties. In fact, finite elements is the reason why we have more advanced structures in aircraft and launch vehicles. Is because we're able to tailor these designs prior to testing, prior to execution in real life. We can actually do a virtual test through simulating these vehicles, these rockets, these aircraft. We can simulate these things in a computer and find out what's going to happen before the test. That's my greatest joy in this area of expertise, is that before the test, I make a prediction using finite elements. This is what's going to happen to this structure. This is how it's going to fail. It's going to fail here or here. I go to the test, and I find I'm wrong, right? That's one option. Another option is that I'm right, and that's an exciting day also, right? Both ways is exciting. If you're wrong, it's exciting because you will learn something new. And if you're right, it's also exciting because it proves that you can actually simulate and predict these things, okay? FEM has all these features. It can be applied to any problem. That's one thing. It can facilitate the modeling of complicated geometries, right? When you went and took partial differential equations, you probably solved very simple domains, a square domain or a simple partial differential equation. With finite elements, you can solve this same partial differential equation, but for a much more complicated domain, like an aircraft. I mean, that's quite amazing that we can solve a partial differential equation for a whole aircraft, right? In a, I would say, simple way. It's not simple, but the software does it for you. And my goal is to teach you what the software is doing behind the scenes. Okay, that's part of this class. It allows you to specify boundary conditions, how to apply the loads, how to apply the pressure, like in the wing, you know, how you apply the lift, right? How you apply the bending moment. You can deal with different material responses for composites, for metals. And the FEM model, the cool thing about finite elements is that when you model it, you actually see the structure. It looks like the structure that you're modeling, okay? Like if you're modeling an aircraft, that's what you see. You see an aircraft. And if you increase the accuracy of the solution, all you have to do is to refine the mesh by increasing the mesh density. Now, I'll discuss this as we move forward in this class, if it's not clear to you at this point. So what is the goal in a solid mechanics problem? So I have a cylinder. This is actually, a rocket part, so it's a cylinder. And I apply a load through this section. So when I apply a load, what I'm looking for is what are the deformations? What are the stresses? What are the strains? Why? I'm not doing it just for fun. I'm doing it because I want to know when the structure breaks. That's what allows you to design a structure, is to make sure that the design that you're given is adequate for real life application. You don't want to go into $1 million, $2 million test without knowing whether the design that has been proposed works. Because if you do that and it fails, you've already have invested $2 million. Now you have to redesign and start over. That's what the powerful things of finite elements. You can simulate these conditions in a software at the very beginning of the design phase. And not only that, subsequent, after production, say you have an aircraft and there was a hail impact and there's damage, or there's impact damage, somebody dropped a hammer, or the catering company that delivers food to the aircraft bumped the aircraft and caused damage, which it has happened. Well, you can simulate these things using finite elements, right? And you can gain experience about what could be happening in there, right? And so the goal there is really to find out when structure fails. That's what we're trying to do with solid mechanics. In some cases, what we're looking for is when the structure buckles, or what is the deformation too much. In a heat transfer problem, sometimes the heat transfer problem feeds into a structural problem, like a nozzle of our engine, right? The nozzle of the engine experiences high temperatures, and these high temperatures produce thermal stresses into the metallic components of the aircraft. So in those scenarios, you want to make sure the structure does not fail due to the high temperatures, right? So that's where you will be using finite elements for. You can also show you here what we're trying to do with solid mechanics. Okay, these are equations, but don't worry about it. I'll simplify it for you. There's 15 equations in elasticity, 15, to solve a 3D problem. Okay, stresses, those are the equilibrium equations of elasticity. Okay, and that's discussed in my finite element book. You can go through that. You have the constitutive law, how the stress relates to the strain. So here is the most general form, but don't freak out. You know, stress equals E times epsilon for an isotropic material, one-dimensional structure, sure. And then you have how strains relate to displacements. So you have a total of 15 equations, 15 unknowns, and you have to solve them all for a complex domain. Can you see the complexity of what we're talking about? You can solve some of these equations for simple domains, like a cube or cylinder, and there's more advanced solutions that are covered in another course here that will give you closed form solutions for various situations. But if you want to solve this for an aircraft or a rocket vehicle or for a building, then you cannot do this by hand, all right? And so to tackle this problem, I'm trying to give you basically a sequence of events on how we use finite elements. You first formulate a systematic solution for how to solve the partial differential equation for a simple subdomain. So hey, I cannot solve it for the whole aircraft. I cannot solve it for the whole rocket or the whole building at just one shot. But what I could do is formulate the solution for a simple triangle or a simple square. Things that look repetitive, right? These geometries look repetitive. And so if I can break up this domain, say I have this domain, and I break it up into small triangles, and I know how to solve the partial differential equation for each triangle, then what I could do now is to assemble how each triangle interacts with the next one, next door, and I can assemble how the system behaves. And what you see here is the subdomains. These little triangles are the discretization of this bigger subdomain, right? And that's what I'm talking about here. I'm talking about breaking up the big problem into smaller problems that are easier to tackle. And if I can do that, I may be able to succeed in basically solving this PD for this whole structure. Another thing I want to point out is that there's types of elements. You can idealize a structure with a 1D bar. For example, right now you're sitting in a chair that has, basically 4 bars supporting you. Well, I could use 3D elements to model that, or I can use a 1D element. I think I'll use a 1D element for that. You have a plate, this table right here, right? This table right here can be represented as a 3D representation, but that will consume too many elements. Maybe instead I'll use 2D elements that represent the mid-surface of this plate. Because maybe I don't expect the plate thickness to change very much. And so what you're trying to do here is you're trying to idealize the physical problem into a problem that can be solved in an easier way. That's really the goal here. And not only that, efficient way. In industry, what I'm seeing a lot now with the computational power that we have these days is that I see models that are millions of degrees of freedom for something that could be solved with less amount of elements. And so when I'm old school, so I'm using elements where I need them, right? Or I represent them in a way that will get me to solution a little bit faster. And the advantage with that is that you can do more sensitivity studies. You can study the structure a little bit better, right? And so if I look at this particular problem that we talked about here, I developed the solution for simple elements I know, and I've discretized it here, going from CAD to this discretization here, right? I'll go from there to applying boundary conditions. Say this side here is fixed. This side is fixed, and I apply loads here. I can easily do that with finite elements because I can apply them at nodes with loads, and then I can put boundary conditions on the left-hand side. We call this the pre-processing phase. All of these I've shown you is pre-processing. But at the end of the day, what I'm really doing, and this is where the miracle happens, is I have this complex set of equations, 15 of them, with 15 unknowns, and I'm making them into a system of linear equations, KU equals F. So I've taken a partial differential equations, and I've turned it into a simpler system of linear equations that can be nonlinear. You can solve also nonlinear, but it's not hard. But you turned a very complex problem into a simpler, you can tackle that. I can tackle that bottom one quite easily, right? All I need is a solver that can invert K, and then I can solve for U the displacements. And if I know the displacements, then I know the strains. If I know the strains, I know the stresses. And if I know the stresses and I know the strength of the material, then I know whether the structure will fail or not. And then I can take these results that I've gotten, the stresses, I can plot them. So I can see visually where the stresses are worse. And I know, okay, it's near the hole and it's this much. And there we may have a problem or not. Or maybe I have to thicken that plate there because the plate is too thin there and I have a hole there, which could cause the structure to fail. So there you go. That's basically the blueprint, and it shows you that finite elements provides you with a systematic approach of solving a very complex problem into a simpler, more tackable problem. You can also do problems with dynamics, frequencies, and mode shapes. Hopefully we can get there. Let's look at a real example from work, the kinds of things I do. Say I'm given a CAD model, say. We have a CAD model of a composite structure. That's, of course, I'm not showing the whole rocket, but I'm showing you part of it. And so this CAD model, you apply to it stacking sequence, apply thickness, you apply material properties, and then you discretize the domain. See, I went from CAD to discretizing the domain into smaller hex elements, 6-phase elements. And with these elements, I can represent the domain for this composite structure. I go to the lab, I measure the strength of all the composite, I measure the strength of the foam, I measure the strength of all the different constituents of this structure, and I can now use finite elements with applied loads that come from here. So apply the loads, the temperatures, all the different things I need are applied. I ask Abacus, the solver, to tell me the solution. It will run this code, and what the code is really doing is solving that equation, KU equals F. And by solving that equation, now I can look at the stresses in the structure, and now I can say, okay, I think it's going to fail here. I can compare it to my test. And hey, I'm matching. I'm not giving you the full story here, But if you're interested in this, I can give you the paper. I wrote a paper on this particular one, so I can share that with you. But in here, you can see there's a failure here, and also it's predicted there. All right? Does it make sense, the process that we're talking about? Yeah? And in real life, what you'll be doing is you don't stop here. You now look at the margins of safety of the structure to make sure the structure doesn't fail, because that could be your job. It could be to tell the designer whether the proposed design is going to work or not. Okay? You have a question?
Yeah. Sorry if I'm jumping too far ahead, but when I go through, like, I do my basic rudimentary FEM on something, when I go through my mesh, I kind of just do auto mesh and I let it do whatever it wants to do.
Hmm?
Are we gonna like go over like us placing mesh, or like how we want the mesh to look, or is that something, or is auto mesh just something that we?
Yeah. Great question. So the question being asked, your name, please?
Mike.
Mike, your question is, if I were to use a software, Final Element software, I could potentially just click a button that says Auto Mesh, and it will mesh the whole thing at once and run that, versus using a more intelligent way of meshing it so that you're focusing where it matters. And so that's part of what I want to accomplish in this course, and hopefully Leonardo will construct some examples to focus on that. Because in reality, say, in this example, I know from intuition that it's unlikely to fail here and here. So I could have used a course elements here, and then focus my attention there, put more elements in there. So there's techniques that allow you to accomplish that. Okay? You can tie a coarse mesh to a fine mesh, and I have an example coming up, I believe, of that. So what is the basic idea of fine elements? So to summarize a little bit here, what we're trying to do is break up the continuum domain into discrete subdomains. So we're taking the big domain, the whole aircraft, and breaking it into discrete subdomains, each with simple geometry. Maybe it's a triangle, a square, or a tetrahedron. And each of these subdomains are called fine elements. These are the elements that we're talking about, and are connected to each other via nodes. That's how these elements are connected. And if we approximate the solution of the partial differential equation over each element, okay, and we interpolate the solution within the element using the nodal values that correspond to that particular element, then now I apply the loads and boundary conditions. Now what I can do is assemble the whole system together with the loads and boundary conditions applied and solve a system of linear equations that could be linear or nonlinear depending upon the problem. But this approach ensures that you have a way of going about it. Without this approach, it will be very difficult to approach this problem. And I think this is one major reason why fine elements has been incorporated into modeling the heart, simulating the heart, or simulating shoes, Nike shoes, Adidas shoes. Fine elements has been used to simulate, I don't know if you remember when the iPhone could bend, right? They even used fine elements on that. They even had a position, a job, seeking people to apply for that job so they could design or maybe redesign or try to understand why that was happening. Okay? So you can use it for a large, for circuit boards, you can use it for a large number of problems, and know in advance what the problems that you may encounter in real life are. Now, the tool is only good as you are. So if you're applying the tool incorrectly, fine elements will not do very good, right? So in general, finite elements is powerful as much as you want that code to be, okay? And if it doesn't have all the features you need, you can make it more advanced, okay? All right, so moving forward here, continuum versus discrete. I have a continuum structure here, a vibrating string with infinite number of unknowns in this structure of a vibrating string. And what I could do is I can discretize this domain into a finite number of domains for which I can know the solution. And so I'm going from continuum to discrete. That's where the finite word comes from. And the word elements comes from the fact that I have subdomains, and this, for example, one element, another element, and so forth. Okay, so finite elements come from the fact that I'm making a continuum problem into a discrete problem with finite number of elements representing the structure or the domain, which doesn't have to be a structure, can be a fluid, can be other things. Moving forward here, this is an application of finite elements to an aircraft. And you can see here that there's a lot of different details. And with this model of an aircraft, I will not be able to predict whether this aircraft fails because it's too coarse. The mesh is too coarse. And I need to have a coarse mesh for a bigger problem like this, like an aircraft, because it will if I mesh everything to the nth level with millions of degrees of freedom everywhere, then I will not be able to solve these equations efficiently. So what I should do is I can at least apply the loads in the global level using coarse mesh. Domains are relatively large, and predict the loads that are going through each of these sections. And so what will end up happening is that I'll take, say, the wing, and I'll take it separately, and I'll refine the mesh. I'll increase the mesh density for that part, and I'll apply the loads, reapply the loads from the global model to a local model. And that's going to your question, Mike, of strategizing to solving a very large problem like this one in a way that's faster. And to accomplish that, all you're doing is refining the mesh for each of these components in a smaller model. Okay? But you will use the loads coming from here to be able to inform that. Okay? Moving forward here, FEM applications have been used to study, for example, the crash of American Airlines 587. This accident investigation was focused on the lug of this rudder, and they were able to use finite elements to understand the conditions that were present for this failure to happen. This is a Queens, New York, 2001 aircraft crash in November 2001. Okay. And other applications in finite element applications, for example, here, to going back to the question of where should I spend the mesh density. Well, here I'm looking at a failure of a composite joint. So a coarse mesh has been used far away from the area of interest, and a fine mesh has been used in the area of interest. These two meshes have been tied together using capabilities available in Abacus, and now also available in NX-Nastran and ANSYS as well. And so this approach allows you to save a lot of elements, so you don't have to waste them in areas that are not important. And so hopefully maybe we can construct an example in our lab session where this can be demonstrated. I use it a lot. This is a mesh actually I constructed maybe 10 years ago as an example. But what we're seeing more and more is that because of the computational advances, what people do is they click the outer mesh and the whole thing gets meshed. We'll now have a large number of elements, and so maybe it takes a long time to solve. But if you use your elements wisely, then you're attacking the problem where it matters, right? You can also simulate contact between different components, the bolts, the washer, the composite. There's a question in the back. Please state your name and the question.
My name is Lee. I want you give a couple of examples about solid mechanics. Example to apply FEM. I was wondering, will you give for fluid and thermal? Will you give any example or with
Yeah, excellent question. So the question being asked here is, the examples I provided here are examples of solid mechanics problems. And the question is, will I approach other problems like finite elements of thermal heat transfer problems or diffusion problems even? And the answer to that is yes. Some of the homeworks will entail solving by hand a thermal problem, and then we'll try to do the same problem using Abacus, right? So I think is doable, and we can cover that here. All right. Any other questions? Great. We'll proceed forward here. This is a penetration of a particle or structure onto a wing, airplane wing, and this is done dynamically, simulated dynamically in San Diego National Labs. This is 110,000 elements. This is in 2000. I'm looking at, in 2016, I'm looking at models upwards of 10 million elements. So our computational capabilities have increased to the point that I cannot even believe it. In fact, I think I'm maybe getting old, because some of these models, when I used to construct them, I was try to keep them below 100,000. And then right now, I see them this large, and I'm very concerned, and it still runs okay. I'm like, oh, wow, it's fast. So yeah, computational capability, because we can do graphics processing, parallel processing. So all this computational capability has also increased significantly to the point that we can solve problems that are quite complex and relatively quickly. I still advocate meshing efficiently, because if you have a problem with a model, you have to fix the model. It's going to take you longer to go through that process. So to me, putting all your brain before you actually do outer mesh, just mesh the whole thing at once and not think about it, to me is more time consuming. I've seen this happen over and over. People will do that. It will take them longer than me. I will spend a whole day trying to think about how to go about it, and at the end I can get to the solution faster, because I'm thinking about sensitivity studies. I'm looking at, not only I can tell the designer there's a problem with the thickness, I can actually change the thickness and quickly provide a solution for that. You can do a lot more sensitivity studies, okay? And when I say sensitivity studies, what I mean is I can vary parameters to try to understand how the structure behaves. Because I think that's part of finite elements. Finite elements is not just you run the code and that's it. I view finite elements as a process where you actually get to know the structure. It's like getting to know someone. You run finite elements, and you try to say, okay, I think the structure is going to behave like this. It's going to bend this way, and I think the load goes through this section, but not this section. You're trying to understand how the structure behaves before it runs. And when it runs, you try to look at the solution and see if it makes sense in the first place. That's really what you want to do, and you want to learn about how the structure behaves. The history of finite elements starts even before 1941, but really starting 1941 or so is when the framework method was coined, and it was, by formulating 2D structural problems of assemblies of bars and beams. Later on, Richard Courant, 1943, approximated the torsional rigidity of a hollow shaft. Okay, and so from there he used the triangular elements to discretize the cross section. And later on in 1956, Turner derived stiffness matrices for trusses, beams, and so forth. 1960, it goes on, Ray Clough coins the terms finite elements. That's when it was coined. And then for a few years, people started to write new elements and introduce them based on intuition and physical hand waving. And that's when the first application structure analysis came on board. And then later on, 1963, finite elements becomes getting the respect they deserved from mathematicians, such as Riley Ritz. And later on, 60s and 70s, computer programs start to emerge. Finite element models start to emerge, and start to become an integral part of design and manufacturing. Today's simulation involves millions of degrees of freedom. I see them used for simulating the manufacturing of complex parts, how 3D printing, how the layer by layer can affect the residual stresses in a 3D printed part. We're seeing finite elements being used to simulate heart conditions or how the heart behaves. I can go on, and in honor of Professor Klug himself, he studied the viruses, how viruses behave. That's an amazing contribution. And you can see how finite elements can be used for a wide variety of problems, okay? For a large number of problems. I also encourage you, as you go through this course, once in a while, go to YouTube and play a video, just type in finite elements to see what people do. You're going to see so many examples of different things. And it's going to encourage you to be motivated in this class and continue to learn. The strategy for FEA implementation is really you take the physical problem that you have, and the idea is to idealize it in a way that you can solve it. And so you can choose what details to include or omit. That it gives you that flexibility, right? And so you can select the simulation procedure. Maybe the events you're looking at are slow processes where static is correct, a solution to be using. Maybe the solution you're looking at is a dynamic problem. Maybe you're looking at the bird strike impact of an engine during takeoff. Well, in that scenario, dynamic simulation is more advantageous there. Then you can select which kind of elements you want. Do you want a beam or a 3D solid? How to apply the loads and boundary conditions. You have to make assumptions in all these things. And also, you have to select the material models for the different parts in that structure. The preliminary analysis should always be done. I really think there's a high value in taking a very complex problem and just doing a hand calculation. It doesn't have to be 100% right, but it needs to give you an idea of what's going on with the structure, and I think it can in many different situations. And so you can take this hand calculation and check it against what your model is telling you. If it's 20 times off, something is not quite right. And units can play a role. I'm telling you from my experiences, the units have caused failures in space applications, unit issues. When I say units, I mean pounds versus kilograms or millimeters versus inches. All these units can have, the misuse of these units have caused failures. And so by doing hand calculations and trying to understand what you expect can actually surface these problems early so you can fix these issues moving forward. The FEA solution, you have to make sure that the solution makes physical sense. If I have my cell phone and I'm trying to model how it breaks in half, if I apply a load this way and the structure is bending the other way, well, I have a problem. It's not what I expect. Many different cases I see where the structure is not behaving like it should, and people are not paying attention. They're just taking those results, putting it in PowerPoint, and saying, this is it, I got my solution. No, you have to understand what is going on with the structure. For example, if I have a pressure inside a sphere, I expect the sphere to deform outward, not inward, right? Well, maybe the pressure is applied the wrong way, or the inverse surface, the wrong surface. And so it is important, therefore, to try to see if what you got is what you expected, okay? So making sense of these results, not just trusting the computer just because the computer told you so, okay? Comparing the preliminary analysis to experiments, and thinking and evaluating. That's part of critical thinking, making sure that results do make sense. And then revising and refining. If you need to revise the problem because there's an issue between what you expected, you have to go back. You have to fix the issues. Okay? That's part of finance. I'm trying to teach you all the things I have to go through. It's not just running the code and getting a number. It's about trying to make sure that what you represented in the finite element software not only makes sense, it behaves like you should expect it, and sometimes you don't know how it should behave. In fact, I've been surprised. Sometimes I say, well, this is not how I expected it to behave, but I find that there are complicating factors that came into play that were not intuitive to me. And that's a great experience to have that, because it's eye-opening, and you can learn new things that you were not expecting. Okay? All right. So I'm going to simplify what is this course about. There's a basic FEA procedure, which I'll use over and over and again. But the idea is to discretize the continuous, and I'll repeat this over and over and over. And next Thursday, we have a Thursday this week, I'll ask you, right? Many of you have taken course with me, and you know I'm extremely interactive. I'm not doing it right now because it's a video lecture. I've never done it before. But once I warm up, my questions are coming your way, and I'll make sure you answer. So over and over and over, I'm going to go through these steps. Discretize the continuous body into subdomains, into elements, approximate the local behavior of each element, and then patch it together, assemble the whole thing together, and solve a linear system of algebraic equations that don't have to be linear, that can be nonlinear. And so what I'll do is I'll move into Springs. How you will deal with this in a simple way, Springs. Now, I do caution you that there's a lot more to Springs in this course, and that I will be covering partial differential equations moving forward at some point in this course, and that we'll develop finite elements moving from there. But I'll start with Springs because it's easy to conceptualize and follow. Okay? All right. So now moving to Springs here, and here I have about 67 slides. And what I'll try to do, I'll try to cover Springs the best way possible. If not, we'll continue on Thursday. But that's my goal, is to move through that relatively quickly. And I think we can. So the basis for finite elements. The basis for finite elements is approximation theory. We have to teach that first, approximation theory. However, before that, I want to explain it in a simpler way using mathematical representation, and that can be done with Springs. We can start with Springs because it's an easy enough problem to tackle, not only by hand, but also you can see the process that goes along with Springs to follow that. Spring models. So why are spring models useful? You can create simple idealizations of the structure. So example of 1D structure. I have an aluminum column here and a steel part here. Well, I can take this part of the column and this part of the column and represent them as two springs. One is aluminum, one is steel. I can do that. And so if I fix this side and I apply a load on the right-hand side, I want to know how the system behaves. And so in this example, the spring model can be idealized as two springs. On the left-hand side is fixed. On the right-hand side, I apply a load P. Now you can see here that I have taken the continuous domain, right? Is that true? Is this a continuous domain? Right? But I have taken this problem and broken up into two elements. And so that's what we call it finite. I went from continuous to discrete. So now I have two elements. And now this side is fixed right there. That side is fixed. And on the right-hand side, I'm applying a load P. Now, if I was really interested on how the cross-section deforms, a spring element may not be the best way to go about this. Maybe what we want to do is maybe use a 3D element or some other element. But in this case, we want to focus on how much displacements do I get at each of these junctures, at this point and at this point, for this problem. And so I have two elements now, and between the two elements, you can see I have something called a node. This connects the two elements together. And at this node, I'm applying the load. At this node, we're making it fixed. Okay, moving forward here, I'll repeat this again, but we'll first discretize the continuous domain into elements. Finite elements, that's why it's called finite. I'm going from continuous to discrete, and then I'll approximate the local behavior of each element. That's what I'll cover next. I just showed you how to discretize the continuous body for that column, that aluminum steel column. And so let's move to that one. So I discretize the body. The discretizing the body goes from this structure to two elements. And you can see here I have element 1 and 2. Let me use the pointer here. And then I have Q sub 0 here, which could be the load there. Q1, which is the load here. And then Q2, the load here. Okay? And then I have deflections at each of these three nodes, which we would like to know more about them. So now I have the definitions here. Q's, these Q's here are the global nodal applied loads. So these Q's is where at these nodes is where I apply the loads. And then the D's are the global nodal displacements. So those are the quantities of interest, the displacements here. So now I'm going to approximate the behavior of each element. And so that's what we'll be discussing now. So let's look at the element behavior. So I have a single spring. And I'm not using anything fancy here. I'm not using partial differential equations. I'm going to use just intuition here. This node, I'm going to label it as I. This node, I'll label it as a J. Okay, so when you develop a local element behavior, you try to understand the behavior for that one element. For my PhD thesis, I developed a new element that's in Abacus. It's called a cohesive element. So I started with a simple element, that single element, and I developed the solution procedure for that element, right? And then I took that and then I applied it to the rest of them. So the idea first is to really understand how this element behaves at this level, okay? And so let's look at local equilibrium. Do you agree that summation of forces in one direction should be equal to 0? So the summation of this force plus this force should be equal to 0. Everybody agrees? Wake up. Okay, so we agree also that because of this, the force at this node is the same as this one but the opposite direction. So that's what we're getting here. Okay. The second thing we see here is Hooke's law. There's a way that we can relate the force to the deflection. And so everybody probably knows that the stiffness of the spring times the relative deflection of that spring is equal to the force required to cause that spring deflection. Everybody agrees with this formula? Right. So what I will do now, if del L is a relative deflection, what is that in terms of dj and di? If this moves di to the right and this moves dj to the right, how much is delta L, the change in relative deflection? dj minus di. And so then what I'll look here is delta L equals dj minus di. So I have three equations: equilibrium, I have Hooke's law, and I have displacements. How the displacements relate to delta L. Okay? So those are three simple equations. Nothing too fancy here, but I can put it together, and what I quickly see, if I substitute this delta L here, I get k times dj minus di equals fj, and fj equals the minus of fi. Can you see that quickly, that everything comes together into one single equation very simply? Now, how many unknowns I have here? What is the variable of interest right now? Displacements. So for the single element I have here, what are the unknowns? dj and di. So in theory, what I would like to have is a 2 by 2 matrix that is multiplied to di and dj. You agree? Right? A 2 by 2. I want two equations, and I do have them. I have the two equations here, and what I'll do, two equations here. What I'll do, I'll put it in matrix form. Don't you agree that I can write this in this fashion? So if I multiply this by that equals to that, that's the first equation. And if I put the second equation is basically this times that equals that. So I have the two equations and the two unknowns. Any questions on this? Do you see this is the element formulation for Spring? Very simple. And now I would like to ask you a question. Can I invert this matrix as it is now? Can I invert this matrix and solve for DI and DJ as it stands now? Why not? Sorry? The determinant is 0. So if I multiply, if I find a determinant 1 minus 1 equals to 0, that's a determinant. I cannot really invert this, right? Because this, in fact, the reason I cannot invert it is because I haven't constrained the problem. This is just two springs floating, or a single spring floating in the air. There's not constraint anywhere. So if I apply a load, what's going to happen? Rigid body motion is going to happen. There's rigid body motion. So I have to constrain the problem sufficiently. This is not sufficiently constrained, and then math does work out. If I try to invert it, I can't. The stiffness matrix is singular, right? Another thing you notice here is that this stiffness matrix is symmetric. I have minus 1 here, minus 1 here. If this is going to be true, the stiffness matrix of the system in finite elements is going to be symmetric when the system is conservative. And there's two conditions for that, which I'll be covering that very soon. So here, I call this the element stiffness matrix, this K here. That's the element stiffness matrix. And this one here is the nodal local displacement vector. And right here, you have the nodal force vector. So these are the equation I get for the single element. And so now I want to really look at this local element behavior and see how can I connect it to patch it with other elements I may have in the system. So let's look at everything is here at the bottom, also given to you. And I'll post these notes online for you to read, okay? So that you're quite aware of what we're discussing here. So now let's talk about patching and assembling things together. Now, we talked about element 1. Element 2, that's element 1, and that's element 2. What I would like to do is to assemble these things together, and the question is how we do that. How can we accomplish that? And here, when you see a superscript 1 here, here, and here, and superscript 2 there, what we're talking about is, I don't know if you remember, but we had the aluminum, we had this aluminum and steel column. So we're representing those as two elements, two spring elements. And so that's for the first element, that's for the second element, right? Each of them will have different stiffness. The steel is going to have a different stiffness from the aluminum, as an example. So how to patch it together? In the global system, this is how it looks. In the global system, I have the local element. Can you see here there's a local deflection there of DI1 and DJ1. These are local to that single element there. Okay, but that single element, this deflection can be related to the global deflections, which I'm going to call D sub 0, D1, and D2. And you can see how they can be related. So here, when I look at D1, DI1, which was this one here, I converted that to D sub 0. You can see that there, because that's what that deflection will be. And then I have D1, which represents the deflection of this middle node, which is the same for this guy and for that guy. You see that? And then for this guy here, which is DJ2, that's the deflection of the second element of the second node. That's also the same as D2. And you can see quickly how D1 is in common to both of them. Okay? Common to both of them. Finally, what we have here is a force vector, which I haven't touched or discussed yet. What I'm going to do next I'm going to do global equilibrium. And I'll ask you a simple question. Would you agree that, so if I have a force in this element acting here, I have that force acting in that node in this, for this element, and I have a force acting on this node on this element too, that the force of these two internal forces added together should be equal to the external force Q by equilibrium. I have to be able to add these two forces and get the external force Q. I have to be able to do that for equilibrium to work out. Not only that, this Q sub 0 must be equal to the force at this end, and this Q2 must be equal to the force at this end. Because of this, what we can do now is, and that's exactly what I'm explaining here, what I'm going to do is a trick. You saw that I had two separate stiffness matrices, one for element 1, one for element 2. What I'm going to do is I'm going to try to combine these together in a smart way. So let's see how we do that procedure. And so to do that, I have element 1 and I have element 2. Okay, so and we already converted these guys to global degrees of freedom. These are the global deflections, right? We converted those to global now. You saw that we went from local, right? We went from local, okay, local to global. How the local deflections of this element relate to the global deflections, because at the end of the day, what I want to do is solve for the global deflections. That's really what I want to do. Okay, so to get there, what I'll do, I will expand. I'm going to do a trick here. Nothing to be concerned about. All I'm doing is, my previous equations look like this. D sub 0, D1, D1, and D2, right? But what I really like to have is a 3 by 3 matrix that has all the deflections, D sub 0, D1, and D2. To accomplish that, what I'm going to do, I'm going to add a fake row here of zeros to have D2 here, and a fake rows of zeros here in the first row with D sub 0. So that now I have a 3 by 3 matrix. And so what I'll do, you'll see here, I added a row of zeros there, which was not present, right? I can do that. I'm not doing anything wrong there. And then I'll have another one, rows of zeros here, because element 2 did not have D sub 0. It didn't have that degree of freedom, right? Hopefully you're following what I'm saying. And if not, we can discuss this, or if you have a question now, please ask, because maybe others also have the same question. So what you see here now is, what I will do is a trick. I'm going to add these two matrices together. And by doing so, you can see here quickly, this one plus that one is what? Q1, right? Sorry, Q sub 0. Q sub 0. This one plus that one is Q sub 0. This one plus that one is Q1. This one plus that one is Q2. And I can add this 1 to 1 easily. And so what you see here is the addition of these two matrices just right there. Okay? It's a simple process. Is everybody tracking? Do you track this? Okay, so let me ask you this question. If I try to invert the stiffness matrix, can I do that? I haven't applied any constraints, so if I calculate the determinant of this matrix, what will I get? 0, which means that the stiffness matrix is singular and I cannot really invert it. So if I have two springs, they're connected together. Right now the two springs are connected. But if I apply a load, that spring has no constraints. I can get any solution I want. And so the trivial solution can be anything, basically, right? Right, so let's see. So if I do, yeah, so given the set of forces, maybe I have a constraint, then I can solve for the deflections, right? You see what I'm saying? I can apply forces, and if I have a constraint, I can solve for D1 and D2 as an example. But a solution exists only if k is invertible. And so what I've told you basically is if I calculate a determinant and the determinant is 0 of that stiffness matrix, then when I try to find the inverse, I won't be able to do it. Right? It will be singular. I can't do it. And so what we call that is that for the two-spring problem, what I have is a rigid body motion. So in finite elements, when Leonardo gives you some problems in the lab session, I will encourage you to maybe don't have any constraints and run it to see what happens. In Abacus, the software is going to say, hey, you have a problem here. This is a singular, there's something going on here where you're not constraining the problem enough. And so what Abacus is doing is really calculating this determinant to find out, hey, have you constrained the problem enough for me to be able to solve it? Another issue you could have is over-constraining too much. We'll cover that at some point down the road. Well, there you see, the spring went running away. This needs to be similar. This was fun. Check this out. It went away, right? It's not constrained. So it's a rigid body motion. Everything's moving together. So let's see here. So for this particular problem, the next step, right? So the first step was what? Approximate the behavior of the one element. The first step actually was to discretize the domain. That's the first step that we did. And we chose to represent it with two springs. That's what we chose to do it. The second step was to approximate the behavior of a single element, how that element will behave. And we did that also. And the third step is to assemble the two elements together, and we did that. The fourth step is to apply the boundary conditions and apply the loads. And so what I'll do, you tell me here in the audience, if I fix this end, what should be 0? This of 0 should be 0. This node should be 0. That should be fixed. And if I apply a load P here, then Q2 must be equal to P, right? Yes? You track? So then, if I know this of 0, and I know this of 0, if I know this of 0, I don't know D1 and D2. I know P, I know the load applied here is P. In Q1, I did not apply a load. If you go back, I did not apply a load there in the center. So Q1 is 0. So this one is known, this one is known, this is not known. This is not known, this is not known, but this is known. So you basically have 3 equations, 3 unknowns. The unknowns are D1 and D2 and Q sub 0. That's the reaction force, basically. The one thing I want to mention to you that's very important, I cannot specify a deflection and a load at the same time, at the same location. And we'll cover that later on when we cover more advanced approximation theory, when I cover essential and natural boundary conditions. You can either specify essential or natural. And I'll cover that coming to that. But at this point, I want you to understand you cannot apply deflections and also apply loads. It's one or the other. Okay? And so for this particular problem, if I know the deflection D naught, in this case it's 0, right? Right? D naught is 0. Okay? That one is 0. I fixed the left-hand side of the spring. I did that. But I'm going to say that for now, I'm going to keep it general. I'm going to say it's not 0. Just in case I give you a problem in the future where instead of fixing it here, I apply a unit displacement or I apply a little bit of a deflection of some kind. I want you to be able to tackle that problem also. And so for that reason, I'm going to keep D sub 0 general for you. So it's non-zero, it's some value, D sub 0. And so what I'll do, my strategy is go to the first equation, solve for just since D1 and D2 are the only unknowns, I'll move this to the other side of the equation. Okay, that's my strategy. On the second equation, I'll move this to the other side of the equation. That's my strategy there. Okay, that way, I basically have 2 equations, this one and the bottom one. And now I can solve for D1 So that's the next equation. So I have the middle equation, I solve for d sub 0 to the other side. And then I have the bottom equation. I can use these two equations now because I know Q1, I know this load, which is 0. I know d sub 0, which is 0 also in this problem. But I could have applied a load there and a deflection there, but for now. And I know this ones and this one. So the only unknowns is d1 and d2. In the bottom equation, Q2 was a load applied on the right-hand side of the spring. And this is known and this is known. The only unknown is d1 and d2. So now I have two equations, two unknowns. And so basically I have two equations, two unknowns. Everything here is known. Everything here is known. I can now solve for d1 and d2, the deflections of this spring system. Is that making sense or not? Yeah? So if I can solve for d1 and d2, guess what? Now I know how the spring deflects. But what if I want to know the forces in the left-hand side of the spring system? So what I had was this, right? I want to know the reaction force there, Q naught. That's what I want to know. So what do? I go back to the first equation. The first equation. So now if I know d1 and d2, I solve for it. I know the values now, right? I know d naught. Then if I multiply the first row by this column, I get Q naught. I get the reaction force. You see what I'm saying? It's a simple process going there. In a more general, looks mathematical and painful, but not really. I'll explain it to you in a way that you follow it. Say you have, I don't know why the text is not showing. Okay, now the text shows up. Okay, good. Let's consider a situation, a rocket problem or an aircraft problem, where you're applying multiple displacements in many different places, prescribed displacements at a lot of different locations of that structure. I'm going to specify that as an overbar. Those are the known quantities. So anything that has a bar on top is a known quantity. The stiffness matrix is known. Okay, the stiffness matrix is known, but you may have deflections that you apply and loads that you apply, and some other things you may not know. What you will do is that you will divide the system equations into two sets. The upper set here is the one with deflections prescribed. So these are vector. So you may have multiple deflections here that are prescribed. Here at the bottom vector are the deflections that are unknown. These are the things you don't know. Okay? And then, as described earlier, if I apply deflections, I don't know the force. That needs to be calculated. In this side, these are the prescribed loads. I have applied these loads and I know them. So you will divide the stiffness matrix in this manner. You'll go to the second equation here, the bottom one, and you will solve. You see, if I take this times that plus this times that equals Q bar, right? So I know Q bar, I know U bar, and I know the stiffness matrices. So all I have to do is solve for U. I don't know what happened there. What happened there? Don't tell me. Okay. Okay. We had a slight issue here. Sorry about that. And then I have to run through the text. Okay. So, so I can solve now for U, which I don't know. I solve for U, get the deflections of the rest of the system, and then the reaction forces are easy to follow. Because if I know U now, I know this one, then I'll have to just multiply the first row times this column here, and then I'll get Q, the reaction forces. So that's the process. And hopefully we'll practice that in the homework also, so you can see how that works. Okay. Any questions on this? Any questions?
Could you explain again how you know Q bar without knowing U?
So these are the actual forces you apply to the system. These are the ones you apply to the system, and these are the applied deflections. You may apply a unit deflection here, a unit deflection there, right? And I'm just trying to explain to you how you will go about it for a situation like that. In most cases, this will be 0. There is a constrained part, and there's no deflections applied. But I do need to explain to you this situation because it could come up. So review, discretize the body, approximate the local element behavior, assemble the global system of equations, or assemble the system together, apply the boundary conditions, and then solve for the deflections. And if you know the deflections, you can find the reaction forces as well. Does that make sense? It's simple enough with Springs. Things will not get simpler moving forward, but as some of you know from 261A. And I also encourage those students from 261A who did great with me and are here to help others also in this class, because it will be a struggle with some of the advanced concepts. All right. Now, there's a better way of assembling things. I don't have to go through those steps of summing forces. Remember, I was trying to assemble the system together? Let me show you that. Remember, I was assembling things together here, doing equilibrium, and trying to figure out how to add zeros. I will add 0 here, a row of zeros, a row of zeros. You know, thankfully, there's a better way, and I'll explain that way next. How to skip those steps so you can quickly get to the bottom of it. And so, remember, finite elements is a systematic approach to solving partial differential equations. So if I have a quick way and a systematic way of implementing an approach, coding it up, then I will be successful at solving these complex equations together. And so we need to find that way, and so that's what I'll be covering next here. Okay. So that's the local stiffness. We covered that. That's local stiffness, and there's a local load vector. That was the global stiffness. You have the first equation and second equation, the first degree of freedom and second degree of freedom. And you quickly notice that the degrees of freedom correspond to the equation number. So I have d sub 1, that's equation number 1. D sub 2, equation number 2. And so what we can do is directly assemble these things together. And I'll show you how to do that. So let's look at this. Okay, so we're going to call something called the element code numbers. Element code numbers. The local degrees of freedom are related to global degrees of freedom. So I have this di1 for element 1, right? So di1 for element 1. So I had this. For general element, right, I had di element E and dj element E. I can relate that to the global system, to the degree of freedom in the global system. And so in this case, di of element 1 relates to d sub 0. Okay? But since it's constrained, there's no degree of freedom. You agree? If it's constrained, that's not a degree of freedom. So there's no equation number for that. For element 1 and element 2, you see there the second node of element E in general, that node corresponds to the center node there. That's this node here, which has degree of freedom 1. I'm going to call it number 1 here. And then the right-hand side is degree of freedom 2. I have 2 degrees of freedom, right? One of them is fixed out of the 3. And so the way I can assemble it is constructing this here. So for element 1, which is this one, has a local number of I and j. We covered it. For every element, basically, I have a local number of I and j. And the global number, you can see here is 0 and 1. 0 and 1, and 0 because it's fixed. So for the nodes that are fixed, we're going to assign them 0. For element 2, I have 1 and 2. So that's 1 and 2 right there. That's element 2 right here has nodes 1 and 2. We call this the element connectivity. These are element connectivity. These nodes tell me how element 1 is constructed. Okay? And so element 1, basically the code number is 0, 1. And for element 2, the code number is 1, 2. So I just taken this 0 and 1 and put it next to each other. That's all I have done. So to explain the process on how to assemble it, I will show you graphically what to do. So you will take the stiffness matrix for the first spring element, and I'll put 0 and 1 here and 0 and 1 here. For element 2, I'll put 1 and 2 here, 1 and 2 here, following this element connectivity, okay, information. And so then I'll construct the stiffness matrix. How many degrees of freedom I have now? 2, not 3, because the one on the left-hand side is fixed. So I only have 2 degrees of freedom. So that's a 2 by 2 stiffness matrix, and is 1 and 2, 1 and 2. So all I have to do now is to run through here and find 1, 1. So where do you see 1, 1 there? The location 1, 1. Oh, 1, 1 only shows up here, right? So I'll take that. I'll take that. Where do you see 1, 1 here? Right there. So then I'll take that one plus that one and add them together and put them in box number 1. That's the first step. Then I go and look at location 2, 1. Do I see anything here that has 2, 1? Location 2, 1. No. Do I see anything here that has location 2, 1? Yes, I see that guy there. And that's the one I select, and I put it in there. Then I run through the same process, 1 and 2, and then 2 and 2. It's symmetric. And so now what I've done, I did the thing that I did earlier, remember? I was adding zeros, and I was trying to add it together. This is the fastest way to do it. But now that's just the K, the stiffness matrix. I haven't shown you how to do the force side of things, but it's also very simple. Let's look at this example here. In this example, I have 3 springs, and I'll apply a load on the right-hand side. Okay, this side is fixed. Okay, how many elements do I have? How many elements do I have here? 3 elements. Wake up. 3 elements. 3 elements here. How many nodes do you see? Global nodes you see. I see 5 nodes. And this side is fixed. How many degrees of freedom do I have? 3 nodes. Excellent. Excellent. So I have 3 degrees of freedom, and I load applied P here. So for stiffness number 1, if I claim that this center node is D1, degree of freedom 1, and this here is element 2, sorry, degree of freedom 2, then what is a code number for element 1?
0,
0?
1.
1. No, 0, 2. Because this is degree of freedom 2, and element 1 connects 0 with 2. Okay? You see what I'm saying? What about element 2? Element 2. 0 and 1. And for element 3? Mike? 1 and 2. Okay? You get it? All right, let's see. I got it right. Everybody has an A now, so far. So for element 1, 0 and 2, element 2, 0 and 1, element 3, 1 and 2. Okay? Then, how many degrees of freedom I have? 1, 2, and 3, but not really. These 2 are the same. So I really have 2 degrees of freedom. This one here and that one there. You agree? Yeah? So then the stiffness matrix that I should get at the end is a 2 by 2. That's what I should get at the very end. And you should have D1 and D2. So let's see how to assemble it together. Let's run through the same process. Well, I gave you the solution here already, but I'll mark it as 1, 2, 1, 2, because those are the degrees of freedom. And I'll search for 1, 1, and I search for 1, 1 here. I don't see it there. I see it here, K2, and I see it here, 1, 1. So these two should be added. These two should be added together and put into that box. Then you search for 2, 1, and then here, I see 2, 1 here. I don't see it anywhere else, so that's that number. It's symmetric. Then I look for 2, 2, and 2, 2 also shows up here, right there, and right here. So then I have those two added together. You follow the process? You follow it? That's how I assemble a stiffness matrix. Any questions on that? Let's move forward here and let's look at the loads now. So do you agree in this example that in degree of freedom 1 there's no load applied? So that's 0. Do you see here that in this side there is a load applied, and that's P? Right? So now all I have to do is solve for D1 and D2, right? Because this is multiplied by D1 and D2 equals to 0P. All I have to do is invert this and solve for D1 and D2. That's all I have to do. Any questions on that? I can get the deflections here and here by simply inverting this and multiplying by Q, right? I see some confused faces, so I'll write it out so to make sure you understand. So I have the K matrix here times D1, D2 equals 0P. I invert this, multiply by that, and I get D1 and D2. And I don't know what I did there. Okay, good. Brought it back. Any questions with these examples? To get the reaction forces at this end, right? At this end, the reaction forces at this end, that's not difficult to do. Because I know, if I want to know the reaction force here, right? All I have to do is multiply K1, this stiffness matrix for K1, that one right there, times D0 times D2. That'll give me the reaction force right here that corresponds to this end. I already know D sub 0. What is D sub 0? Huh? 0. How do I know D2? How do I know that one? I already solved for that here, earlier. I know D1 and D2. Take the D2, put it here, and then now you can get the reaction force on that end. Does that make sense, guys? Everybody follows? Yes? Excellent. This is just a summary of what I just explained. This is a faster way to do it. You can go straight for it a little bit faster. I'm going to give you a 2-minute break for you to breathe a little bit. And then we'll come back here. 5:37. 5:38. Actually, it's 5:35, so 5:37. I don't know why. Okay, I want to solve the same problem that we just discussed with spring elements with energy approach, using energy principles. With the energy principle, we will use something called the theorem of minimum potential energy. And what this theorem says is that the equilibrium shape, the shape that's in equilibrium of the structure, is a shape that minimizes the total potential energy. And this only works when the system is conservative in two ways. The deformation is elastic. What that means is when I apply the loads to the structure deforms. When I remove the loads, the structure basically comes back to the original deformation, original shape. So that's what an elastic structure means. Also, when there's no Fowler forces, what that means is when the forces do not depend on the deflections. An example of that will be a beam. If I have a beam here and I apply a load this way, if this beam deflects this way, that the direction of the load is not changing. It continues to be applied downwards, not following the deformation of the structure. In this case, the system is said to be conservative if the load applied does not depend on how the structure deforms. In these two cases, you can use this theorem called minimum potential energy. And this theorem allows you to find the system in equilibrium by minimizing the total potential energy. And so to look at that, the total potential energy is made up of two things. The strain energy stored in the system plus the work done by the external loads. So you have these two quantities that when added together give you the total potential energy. Minimizing this function with respect to the unknown quantities will provide you with the deformations of the structure that represent the equilibrium state of that structure. Okay? And so let's look at for a spring. I want to ask you guys, what is the strain energy of a spring? Does anybody know? So if I have a spring and I apply a force F and it deflects an amount delta L, what is the energy in the spring, strain energy? 1/2 E epsilon squared. But the stiffness is K. So K delta L squared, right? So very close. Thank you very much. So 1/2. So for the example, simple example, I have a spring with a load applied P, right? You agree? K, simple, right? Very simple. The total potential energy is as simple as 1/2 K delta L squared. So that's the energy stored in a spring. And you can see that's area under the curve also. Minus the load applied on this end, P times the amount of deflection you have. That gives you the total potential energy. If I take the derivative of pi with respect to delta L and set that equal to 0, I should be able to find the minimum of this total potential energy. And so let's look at what we get. If I do that, I get K delta L minus P equals 0. Isn't that what I got earlier with the equilibrium equation? Do you remember it? I wrote that expression earlier. Simple. But I got the same thing I had derived earlier. Example 2, 2 springs. Remember? We covered this one with the 2 springs. In this case, I have element 1 and 2. So for element 1, I have 1/2 K and then have the stretching of that spring squared. Well, the stretching of that spring is basically dJ minus di in general. That's what you should have, right? So the relative deflection of one end versus another, the difference of those squared should give me the strain energy of a generic spring altogether. For this example of the 2 springs, I have work done here, P times D2. So that's the work done by the external loads. And so that's what I will have here. That's it. So I have PD2, that's external load, which is right here. For the first spring, there is constraint on the left-hand side, so it's D1 minus 0 squared. For the second spring on the right-hand side, is D2 minus D1 squared. That's the strain energy. That's the strain energy of these two springs. Okay. Any questions on that? It's very simple, right? But if you have a question, if you don't feel I explain something that and you don't follow it, please ask me the question now, because maybe others also have the same question. Okay. So now to find this the minimum potential energy. When the potential energy becomes minimum, because that represents the state at which the system is in equilibrium, what I'll do is take the derivative of pi with respect to D1, set it equal to 0. Take the derivative of pi with respect to D2, and set that equal to 0. And when I do that, guess what I get? I get the same equations we got earlier. So I'm getting the same solution that I got earlier not using energy. And so it's really cool to see how energy methods can give you very similar results to using equilibrium equations as you know it. Okay? So all I did here is the operations. You guys, if you can work it out at home, you'll get what I got here at the bottom. But I encourage you to go through this process and do so. Okay? Just go ahead and do so. So it's 10 points extra credit if you do that, and you bring it next Thursday. Okay, so just go through that derivation. One thing I do in this course very often, ask to my students here from 261A, I give a lot of extra credit, and you should take advantage of it. It does help a lot with a grade, and also it helps you learn quite a bit. Okay. The total potential energy in general has a quadratic form. I won't cover this in extensive detail here, but it does have a quadratic form. I have two proofs that provide here that you can go through at home, showing you that this quadratic form gives you this form, which is basically the strain energy of a spring. And so I want you to go through the derivation. It's quite simple, and you can actually derive it in a straightforward fashion. And also the global equilibrium, if you directly differentiate these equations, you'll find that you get KD equals Q, which is what we got with these two examples I showed you. I'm not going to go through these two proofs right now. Let's continue moving forward. The bottom line of this particular short lecture I just showed you is that using energy methods will give you the same answer as using an approach based on Newton's law, basically. And you saw how the two examples matched the earlier examples given with equilibrium approach, using energy methods. And we'll be using energy methods in this course quite a bit, and you will see that coming forward, moving forward. So let me move next here, application to bars. How I can use springs to approximate bars, and I will do that now. So I have a naturally discrete body. The body it was aluminum and steel, but let's say, for example, now this whole thing is just one structure, and it's naturally continuous body. It's basically a body like this with a distributed force like that. A distributed force here of Q naught. And say the modulus is changing. Say the modulus changes from left to right, like that. And say the cross-section is constant. A structure like this with the modulus is changing now may be possible with 3D printing technology, where you can actually increase the density of one metal that you fuse against another metal that you're fusing. And so perhaps you can achieve this kind of modulus variation. But for me, this example is more illustrating how to apply springs for this problem in a simple way. So how to represent it? So let's start with 1D elasticity. In 1D, stress equals E times epsilon. Everybody knows that in this course. And if you don't know this, please review Mechanics of Materials book to come up to speed. you can also find the strains. The strain equals du dx. If I use, I take a small length here, delta x, and I make this line move an amount u, then there is a differential movement of delta u. Well, strain equals the change in length, which is basically this minus that divided by original length. So I get delta u divided by delta x, and when I find the limit, I get du dx. Epsilon x equals du dx. So for uniform bar, the change in length divided by original length is the strain basically. The stress equals P over A, and now stress equals E times epsilon. So I'll substitute stress there, and I'll substitute strain here. So if I do that, now I can calculate the effective stiffness of this spring by simply rearranging everything. So if I have P over A equals E delta L over L, all I have to do is bring this A here, so I have EA divided by L. And so EA divided by L is your K, basically. This is K, and there's delta L, and there's a load P that acts to stretch that bar. So now I have come up with the equivalent representation of that stiffness of the spring as it relates to a bar. Okay, so spring stiffness is EA over L, and it depends on the cross-sectional area, the modulus of the material divided by the length of that bar. Does this simple explanation make sense? Okay, so we're going to use this to represent the stiffness. So I'll take this basic FEA procedure, which I'll repeat over and over and over. But we're going to discretize the domain. That's the first step. Approximate the local behavior, patch it together. Those are the steps. And how do we do that? I'm going to divide it. I choose to do this. You can divide it into 10 elements if you want. But for the purposes of this lecture, I divide it into 4 elements, 1, 2, 3, and 4. 4 elements. And so the question is how do I define the case? I already showed you how to define the case to some level. This constraint on the left-hand side. So if I have 4 elements, I constrain on the left-hand side. How many degrees of freedom you see here? Left. 4. 4. Everybody's with whoever said it was 4? You agree? 4. Very well. So we can see E changes as I move from left to right, and A is constant. So I have to really figure out a way of tackling that. The code number is easy. For element 1 is 0, 1. For element 2 is 1, 2. For element 3 is, and so forth. So you can see the code number is written here. It makes sense because the stiffness matrix that you get at the end is 4 by 4. Now I approximate local behavior. Now I have to figure out how to deal with this. I have an element out there. So what I'll do, I'll take, do you agree that the modulus varies from left to right? So one way, what I could do is to basically take the average modulus between this point and that point. That's one approach to do it, right? And then use that to represent that spring stiffness. Then remember the spring stiffness is EA over L, remember? EA over L. I can choose an E that represents the somewhere in between, in the middle of each section that I broke it into. Okay. Another thing you see here is that now not only I have concentrated forces that could apply, but now I have distributed forces, distributed external forces coming from this Q here. You see this Q being applied? What I could do is, for that Q, what I could do is take half. What is the total force on that bar? Q times what? The length of that, right? So I can take Q times the length of this element and put half there and half here. That's one way to do it. And that way I can apply, in an easy way to do it. So let's see here. That's what I did there as an example. So if the element length is L, I can take Q times the element length, put half here, put half there, and that way I've tackled that problem there. For the modulus, like I said, one approach is to use the average the location between where the element starts and the element ends. Okay. And then I can calculate K from that. EA over L. Okay, EA over L. Any questions on that? Any questions on that? So now I have the local element behavior. You can see here the local element behavior has these extra forces that you had not seen before. These are coming from the distributed forces, QL over 2, QL over 2. And then these ones we're going to assemble together next. And then again, the modulus I'm going to use to define this K is the average of each element. Okay, that's the way I'm doing it here. And then the stiffness is EA over L. Okay, so then I move now to patching everything together. And that's easy because you already learned it. The spring element 1 is 0, 1, 0, 1. Element 2 is 1 and 2, 1 and 2, and so forth. Using the code numbers, now I can assemble it. There's 4 unknowns, right? We said there's 4 degrees of freedom. I can easily assemble the stiffness metrics together using the procedure that I've showed earlier in the class. Is that clear, what I've covered so far? And now all I have to do is assemble the global forces. And what you see is that you can have concentrated forces or distributed forces. Earlier, I only talked about concentrated forces, but now I also have distributed forces. In this example, did I apply any concentrated forces? No, I didn't apply any concentrated forces in any of the nodes. I just had a distributed force along the bar. So this column is basically 0. This is the only one that I covered for this example. And I basically took the Q times L divided by 2 and put it on each end. I do that, and so for element 1, I have QL over 2, QL over 2. Same for element 2, same for element 3, same for element 4. And I put the code number for each element right there. Right there. Right? And then to assemble it, all I have to do is I have Q1, Q2, Q3, Q4. I number it 1, 2, 3, and 4. Where do I see 1 there? Here. Do I see any 1s here? Yes, I see it there. So, but I don't see it anywhere else. So I take that and add it up. And that's what I get. One that could be interesting is element 4. Element 4, the fourth number 4 does not show up anywhere except here. So I get QL over 2. Now this L is the element length. The total element length of the thing was L. So if I have 4 elements, each L is L over 4. You agree? So L over 4. All right, so I have the Q, I have the K. So I have this Q. And I have that K. With the K and the Q, now I can solve for the deflections. Let me just quickly finish this one here. So I have K, fully defined. I have Q. Then I can solve for the deflections. The 0, remember, that's a constraint. So the constraint does not get assembled. Okay? We covered that in a previous example. You follow? The 0 does not get assembled. Finally, the summary and review for this section is we can represent a continuous body into spring elements for a one-dimensional bar. And we have a process of doing so on how to also deal with distributed forces, distributed loads. You can basically assign the loads in a smart way, right? With Abacus, moving into Abacus, I'm not going to spend a lot of time here because Leonardo is going to do that in the lab session. But I want to show you a sample Abacus input file of this example problem, the 2-spring problem. And you can see I define the nodes, I define the element connectivity. And when you go and study that, the stiffness of each spring, I made it 10,000, I made it up. I apply the boundary conditions on this node, and the loads on this right-hand side of 10 pounds. And so the idea is to solve for D1 and D2, and that's how you'll write it out in Abacus. You can write it out yourself. And at the end, you get the solution to the problem, which is given here, the deflection here in the center and the deflection here at this end. And I'll let that part of the discussion be taken care of on Friday more. But for this, I just want to show you that you also will have this for you to study. Okay? With this, I'll conclude today's lecture, which did go for 2 hours, and that is how my lectures are. They will be intense, and it will go from top to bottom. Okay. With that said, thank you for your time, and you have a great day, and I will see you Thursday. And if you have any questions, I'll be here as much as you want.